Welcome to another new video of interesting math problem on our channel Math Solutions for You. Please do like, share, comment, and don't forget to subscribe to our channel. A rather interesting problem that I came across recently, and this particular problem is a multiple choice question that asks for the number of integer solutions to the equation x to the power x is equal to x. So this is a very interesting equation in itself. Obviously, it involves exponents, but the variable is present both in the base as well as the exponent. So that's where it looks rather intriguing. So in order to find the number of integer solutions, so we start with, sort of a trial and error approach. So what we do is we start with x equal to 0 and we try to see what x to the power x is. And x to the power x is 0 to the power 0, and 0 to the power 0 is kind of a controversial quantity, but I think the commonly accepted value for it is 1. So for x equal to 0, x to the power x is 1, so clearly it does not satisfy this relationship of x to the power x equal to x, because in order to satisfy that, x to the power x would have the same value as x, and in this case x has the value 0, but x to the power x has the value of 1, so the equation is not satisfied. So that's kind of a method of testing, and now we go ahead and test x equal to 1. This is kind of obvious, x to the power x is equal to 1. So in this case we see that x to the power x equal to x is satisfied because x to the power x is the value 1, which is the same value as that of x. What happens if I take x equal to 2? Well, then x to the power x becomes 4. It becomes considerably larger, and this is mainly because the exponent kind of grows and that exponent effect takes over, so x to the power x gets away very quickly, and that's more evident when you test higher values of x equal to 3, x to the power x grows even larger to 27. And that's all we need to test. We don't need to go any farther. Now, what the problem asks for is number of integer solutions. And so far, we have considered 0 and positive integers. But integers can be also negative. So negative numbers like -1, -2, they are also called integers. So that's kind of important thing to keep in mind for solution to this particular problem. So let's test some of the negative values and see what's the pattern there. So if I let x equal to -1, I have x to the power x is equal to -1 to the power of -1. So that's kind of interesting, right? Now, in order to evaluate this, we have to remember that any negative index or any negative exponent simply means it's the reciprocal. So if we take 1 divided by that quantity, and then we can take the exponent as positive, right? So we basically have -1 whole to the power -1 is equal to 1 divided by, so we're taking the reciprocal, 1 divided by -1, and now since we're taking the reciprocal, the exponent or the index will be positive. So we have 1 divided by -1 whole to the power 1. And -1 whole to the power 1 is simply -1, so we have 1 divided by -1, which is -1. So here we note that if I test the value of negative integers for x equal to -1, I'm getting x to the power x is equal to -1. So I have another solution to this, right? Because x to the power x is the same value as x for x equal to -1. Now, are there any other values outside 1 and -1 that can satisfy this relationship or this equation x to the power x equal to x? And remember, we are only considering integer values. So let's see what happens if I take x equal to -2. Then x to the power x becomes -2 whole to the power -2. And again, negative index or negative exponent means reciprocal. So I take the reciprocal, 1 divided by -2. And now my exponent becomes positive in the denominator. So I have 1 divided by -2 whole to the power 2, right? And this becomes 1 by 4. So the value, the magnitude-wise, the value kind of shrinks, right? Value of x to the power x. And if I take x to the power x equal to minus 3, then x to the power x becomes minus 3 whole to the power minus 3. And again, if we evaluate this, this becomes 1 divided by minus 3 whole to the power 3, which is minus 1 by 27. So what we see is as x becomes more and more negative, the magnitude of x to the power x, if I ignore the sign, the magnitude of x to the power x gets smaller and smaller. It shrinks more and more. But depending on whether x is even or odd, it will oscillate between positive and negative. But the magnitude, the value, the magnitude, the absolute value, that goes down pretty drastically. And it's evident because the denominator, so when I do the reciprocal 1 divided by whatever the denominator is, the exponent of the denominator becomes larger and larger as x grows more and more negative, right? So the value continues to shrink, the magnitude continues to shrink, right? And so there can't be any possible solution there, because as x grows more and more negative, the magnitude of x grows, right? The absolute value of x grows, but the value of that quantity, x to the power x, that one continues to shrink in magnitude, and it will keep on oscillating between positive and negative depending on whether x is even or odd. So that's what happens when x goes onto the negative side. So from this pattern, we can safely conclude that there will be just two solutions to x to the power x equal to x. And of course, I'm talking only about integer solutions. So one solution is x equal to 1. The other solution is x equal to minus 1. And this is not required, but you can actually, if you plot this graphically, and I actually used a computer program to plot this, to make these graphs so that it becomes even clear that these two are the only two solutions, integer solutions of this equation. So this is the graph so I have basically two graphs here. The one in red is of the function y equal to x to the power x. And I have only, plotted integer values of x here. And the blue line that you see, that of course is, is the line, is a straight line y equal to x. So I have two graphs. And the solution of this particular equation, x to the power x equal to x, will be at points where these two graphs meet. And it's pretty clear that the only 2 points where these graphs are going to meet are at x equal to minus 1 and x equal to 1. Now, see what happens as x becomes more and more positive. Like I said, the graph, of y equal to x to the power x, so the red graph, it kind of moves more and more away from the blue graph, right? So there is no meeting point there beyond x equal to 1 on the positive side. So what happens on the negative side as x becomes more and more negative? So you can see that like we expected, the red line, which represents the graph of the equation y equal to x to the power x, so the red line kind of becomes very low in magnitude, kind of almost aligns itself with the x-axis, means it becomes almost 0. It's actually not 0, it's very small, and it will oscillate between positive and negative, but its magnitude becomes closer and closer to 0 as x grows more on the negative side. Whereas, of course, it's pretty evident from the graph of y equal to x, the blue line continues to deviate farther and farther away, right? So graphically, this illustrates that these two are the only two integer solutions of this equation. And again, the graphical part, you don't need it to answer this question, but I just gave it for curiosity of those who would be interested. So the correct choice to this question will be option C. There are two integer solutions to this equation x to the power x equal to x.